This is lesson 8.3. We are on volume and we'll start with the disk method. On your flipbook, it would be the 1, 2, 3, the third flap down where it says disk. When you open it up, it should say definition volume was solid on the top. If you're doing this digitally, this would be page 4 on the digital copy on Canvas. Okay, all right, let's get started. Okay, so this is the page in your flipbook, and so we're going to start looking at this as a function that we're going to revolve around an axis. When you take the function and you spin it around an axis, you will see that it actually will create this three-dimensional figure, and you're going to have to rely on yourself to have a little bit more imagination when you look at something like this. And one thing is that you have to be okay with trial and error and erasing your lines. That's one of the biggest things. All right, so first thing you want to do is you want to graph this. You really want to have graph paper to have a lot of accuracy to see where your graph is, where your function is going to cut one off of each other, and where it's going to make sense. So your equation is y equals root x and y equals 1. So what I'm going to do is I am going to use graph paper. Okay. I'm going to use graph paper and graph this y equals root x. Now, before I start graphing, I'm going to remind myself that x equals root y looks something like this, where it is a sideways parabola going like this. It's a positive root y, right? And then y equals 1 is somewhere over here. And this is about 1 and 1. So it's a really tiny graph. It's really, really tiny. So you want to make sure that either you make your grid a little bit bigger, or you definitely zoom in if you can, all right? So what I'm going to do is I'm going to go ahead and graph this out and start my axis like so. Okay, I'm gonna make it every 3 boxes 1, just so I can see a little bit better of my picture here. All right, x equals root y is gonna be 0, 0, 1, 1. It's gonna curve out like this. And then you have your next function, y equals 1, something like this. And then usually what I do is I use red to show my axis of revolution. I'm going to spin this around an axis. It says it's going to spin around the y-axis. So here's my axis of revolution. I draw a little spin for myself to see it's going to spin around this whole thing. Now, it doesn't matter the direction of your spin, because it's just going to go around and around. But the way I make it so I can see the three-dimensional picture of it is I usually draw the mirror image of it, right? And then I connect the endpoints with ellipses. So notice how these are 2 endpoints right here. If I connect it with the ellipse like so, I can see, if I shade in a little bit, hopefully you can see this is kind of like a funnel, right? With no end at the tip there. Or another thing that I usually use to describe is, there's this thing usually at the mall where you have the pennies you drop in and it goes around, 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 and finally goes down. So this is the thing I usually refer to, okay? All right, so next thing what you want to do is you want to take your graph and you want to take it out, and take your graph and literally cut and paste and take it to your notes here. Okay, so I'm going to paste my image here. Here is my graph. So again, don't make it take up too much space, but you have to be able to see that this is the graph we're working with. Okay, all right. Now, imagine what is happening here. The way this picture is created is by taking many, infinitely many circles and stacking them up. Notice how my circles are stacking up vertically like this. If they're stacking up vertically, then my function is dy, because it's stacking up the vertical axis. Secondly, what am I stacking? I'm stacking circles. So volume of this is simply by taking infinitely many circles, infinitely pi r squared, right? How far am I stacking? Well, looking at my original blue picture here, blue line here, I'm stacking from 0 to 1. So 0 to 1, stacking them all the way up to y equals 1. What's my radius? Well, each of my circles stops right here along this line. So what is this line? Well, this line is my equation, root x here, right? So y equals root x. But wait a minute, since I'm making this go up the y-axis, then my equation has to be in terms of x equal. So first thing I need to do is make sure I change that around. Y equals root x, I can make it so it's y squared equals x, right? So that way if I square both sides, I can have x by itself. Then this is my radius function. So radius, in this case, is y squared. So y squared is here. Okay, now my setup is ready. I can go ahead and use my knowledge of derivatives and integrals to figure this out. I'm going to clean this up. I get y to the 4th dy. So then if I take the antiderivative, y to the 5 over 5, value 0 to 1, I get a simple answer of 1/5. So my answer is pi over 5. And that's it. That's the volume of this awesome funnel-like thing. Okay? Now, at this juncture, we really don't mind that you don't put in the units. You can put units cube if you want, but this right now is just kind of asking you to have an open mind to realize that the volume is created by spinning this this function around an axis, hence creating this circular region that's stacking up and down or left and right. And so we're just getting used to get used to this idea of volume. So the units are very important right now. It will play its role later, right? So right now, just get comfortable with how to solve these problems. Okay. Next picture here says y equals x minus x squared and y equals 0. So here are my two functions here, and we're going to spin it about the x-axis. Okay, again, we're going to use our graph paper to help us. So my equation, again, I usually give myself a little bit of hint to remind myself of what like a plan, right? So planning this. Well, y equals x minus x squared is upside down parabola, right? So it's going to go something like this. And y equals 0 is this x-axis here. So it's going to tell me that that's not going to take a lot of space. Again, this part right here, I know this because I've been doing this for many years. So be okay with trial and error. If you want, you can use your calculator to kind of help you see how big of space you need for your homework problems. But really try to be okay with, all right, I got to graph this out and erase all the extra lines or what I don't need, right? So looking at this, and looking at what I know, I'm going to go 1, 2, 3, 4. That's 1. And that's 1. Okay. All right. So my equation y equals x minus x squared, if I recall, that is a parabola. I'm going to factor on x here. So it's 1 minus x. That tells me my x-intercept is at x equals 0 and x equals 1. So my parabola is going to cross at x equals 0 and x equals 1. Another thing I do know is that my vertex, the tip of my parabola, is going to be halfway between 0 and 1. So x equals 1/2. That's where my the vertex is going to be. So I'm going to take that and plug it into my equation here and figure out what my y value is. So it'll be 1/2 minus 1/2 squared. So 1/2 minus 1/4 gives me 1/4. So my height is just right here, 1/4. Right. So if I graph this out, this is going to be my parabola. And normally, of course, I go all the way down here. But remember, we don't need any of the extra lines. I know my other equation is y equals 0, so that's going to be right here. So that means I don't need any of my extra lines. So that's why I didn't draw these out in the beginning, because I don't need them. Okay, so these are my extra lines. And finally, what is it spinning about? If you look back at our equation, this is spinning about the x-axis. So here's my revolution, axis of revolution. That's my spin. So again, to make myself see the three-dimensional picture, I can see that it looks something like this, kind of like a football, right? It's not perfectly rounded in the sense that it's wider here at the tip and skinnier here at the edges. So it's really like a football. Another way I help students see is like in Sleeping Beauty, the spindle. So if you turn it sideways, it's a spindle, right? All right, so this is my graph here. I'm gonna, again, literally cut and paste. I'm gonna cut and paste this into my notes here. So paste my image. Here is my beautiful spindle, okay? All right, now again, to see the picture, if you need to draw this out, if you don't need to, don't do it because it just makes it a little bit messy. But hopefully you can see it's circles. Again, I'm stacking these circles side by side. Here's my circle, here's my next circle, circles. So I have so many circles, right? So I'm stacking them side by side. Hence, if they're stacking side by side, they're stacking along horizontally. So this is a dx problem. Oops, sorry, that is kind of gross. Okay, so this is the dx problem. Right. Again, I am stacking circles. These are always going to be circles, right? Because you're spinning this around. It's going to be a circular thing. So pi r squared. Along the x-axis, I stacked it along 0 to 1, 0 to 1. It just so happened both of these intervals are the same from numbers 1 and 2, but it's not going to be the way every single time, okay? What about my radius? Well, how high up is my circle going? I'm going up until I hit this line. This line is my equation. So your radius is x minus x squared. Okay, all right, now that I have my setup, the thing about these discs is that most of the time you need to clean up this equation first, your integrand, your function in the integral first, before you take the antiderivative. It'll make your life a lot easier, right? So 0 to 1, if I multiply this out, I get a positive x to the fourth minus 2x cubed plus x, right? So x squared, yes, x squared, sorry. So make sure you multiply this out, and I usually put it in standard form so I don't lose any of my terms, right? So now you're ready to take the antiderivative. X to the fifth over 5 minus 2x to the fourth over 4, so x to the fourth over 2 plus x cubed over 3. Okay. And again, if you're not comfortable with that, make sure you then show every step. It's okay to show more steps. Don't forget plugging your 1 and 0, knowing that plugging the 1 will give me nothing, so which is awesome. You get 1/5 minus 1/2 plus 1/3, right? So what is the common denominator between all these? I would say it's 30. So 6 over 30 minus 15 over 30 plus 10 over 30, so 30. That gives me 16 minus 15, so pi over 30 is my final answer for this volume. Very teeny tiny, and it makes sense because if you look at the graph, you remember that graph, it is much smaller. It's a very, very tiny piece, okay? All right, so now, right, our function is not always going to spin on the axis. So in number 1, we spin around the y-axis. In number 2, we spin around the x-axis. What happens when your axis of revolution moves? What happens if I'm spinning around, let's say, y equals 4 or x equals 2? What happens when it moves? So I give you a little hint here. It says that the rotating axis is a line not the x-axis. So it's a line right here, like it says y equals 4. Then your radius is going to be a top function minus a bottom function, right? If you're rotating right here along a line that's not the y-axis, so it's going to be a right function minus a left function. Exactly like I promised when we're dealing with area, we have top minus bottom and right minus left once again, okay? All right, first thing, let's take a look at this picture because it gets a little bit confusing when you don't know what the picture looks like. Okay, so my equation here, let's see, my equation here was y equals x squared, y equals 4, and you're spinning it around y equals 4. Okay, so again, game plan. Y equals 4 looks something like this. Y equals x squared. Y equals 4 is up here, and my spinning, so I'm going to spin this way, so it's going to look something like that. Again, this is a game plan for myself. Okay, now I know how much room I need. Okay, so I need a lot of y-axis room. Okay, so I'm going to draw my equation. So I'm going to draw my graph here. I am going to have my y-axis this way. Oops. Oop, too much. Okay. Then my x-axis this way. Okay. 1, 2, 3, 4, 5. That's a good enough for me to know what I'm doing. Okay. My y equals x squared. I need 0. 1, 1, 2, 4. So here's my parabola. And this is y equals 4. I'm going to spin it around y equals 4. So here's my axis of revolution. Let's spin around this way. And again, to look at it as in terms of a mirror image, I can see that my graph looks something. This is definitely looking a lot more like a football because this is a lot bigger than the previous one. And again, I usually do a little bit of shading. This is really for me so that I can see the three-dimensional picture. You don't have to. I also think it's pretty, but that's just me. All right, so this is your big, giant almond. So whatever helps you see the picture, all right? So I'm going to go ahead and cut and paste, right? As always, I'm going to cut and paste this and stick it into my notes. Okay, so what is happening with my radius this time? Well, let's take a quick look. Your circles, your circles that you're spinning around, your circles are here, right? This is your circle, right? So first of all, my circle is still stacking horizontally, so this is good. This is a dx problem, right? So that's the first thing I need to know, whether it's a dx or dy. So volume is pi r squared dx, okay? Secondly, it is where is it for my interval? Well, it started at -2 to +2 on my x-axis, so -2 to +2, and then my radius squared. So most important thing is, what is my radius? Well, the radius is this line right here, right? Now that distance is not given by the function. The function gives me this value right here, right? Because your y value is only up to that point right here. But I want this distance right here. So what is that distance? It is simply the red line minus my parabola line. So this is my top minus my bottom. It is the difference between the red line and my function itself. So my radius is top minus bottom, hence 4 minus x squared. 4 minus x squared is my radius. Okay, you got to practice this, especially if the axis revolution moves, then your radius is going to have this top minus bottom or right minus left situation here. Okay, all right. Now that it's set up, same as always, we're going to multiply this out so I can have an easier time with this. So if you multiply this out, you get x to the 4th minus 8x squared plus 16 dx. Okay, and now another thing is, if you notice, this picture is symmetrical. With this method, you can actually do the doubling thing. We can go ahead and double this, and instead of going from -2 to 2, we can go 0 to 2. I can get this right half and then just double it for the other half, right? And then get my full volume. So x to the 4th minus 8x squared plus 16 dx. Okay, now I'm ready. I like zeros. It's a lot easier to work with than -2. Okay, all right, so 2 pi antiderivative of x to the 5th over 5 minus 8x cubed over 3 plus 16x evaluated 0 to 2. Okay, plug in the 2, I get 32 over 5 minus 8 times 8 is 64 over 3 plus 32 minus 0. You don't need to put the 0 in. Okay, so yes, there's quite a bit of calculation here. You really got to get comfortable with adding and subtracting your fractions. I notice again, my common denominator is 15. So if I multiply the first thing by 3, I get 96 minus 64 times 5 is 320 plus 32 times 15 gives me 480 all over 15. So we get 2 pi. Okay, 480 minus 320 is 160. 160 plus 96 is 256 over 15. So I get a really nice answer of 512 pi over 15. Yes, I use nice very loosely. So we're starting to get these really nasty big fractions. Okay. All right. Last problem on the set, we're looking at this function, x minus y equals -1, x equals 2, y equals 1. First thing you want to do is you want to change the function so it's easier to graph. So in order for this to be easier to graph, I'm going to add the y over and add the 1 over. So y equals x plus 1, right? And then it's a little bit easier to graph. Okay, I'm going to grab my graph paper and clean up a lot of stuff I have here that I don't need anymore. Okay, all right. So my equation was y equals, what was it? X plus 1. And then I have x equals 2, y equals 1. I spin it around x equals 2. Okay, so again, game plan. X plus 1 looks something like this, whereas 1 is right, one slope is positive. X equals 2 is a vertical line somewhere here. Y equals 1 is where the axis is. And I spin it around this one. So it's going to spin around like so. So like that. Okay, all right, game plan, right? It's just a really rough sketch of knowing what I need. Then I know for sure I need a lot of my first quadrant, okay? And then if you don't want to change your scale, it's totally fine. 1, 2, 3, 4, 5. 1, 2, 3, oopsies. 1, 2, 3, 4. Okay, so my equation is x equals y equals x plus 1. So I start at 1, slope of 1, 1, 1, 1. So that's my equation here. X equals 2 is my vertical line here. Y equals 1 is my line right here. This is my original piece. Sometimes I go as far as to shade in my original piece because sometimes, I like knowing what my final picture is going to look like, but it's also important to know what my original piece is, especially when you have a lot of lines coming in later on. Okay, you're spinning around x equals 2. So here's my spin, your axis of revolution. Oopsie. Your axis of revolution, right? And then again, for me, for my own personal learning purpose, I see the mirror image and I can see this is actually a cone. right? This is actually a cone. So this is something that we can actually use geometry to check our answer. So it's very nice to do this at the very end to really show you that this actually works. Okay. All right. So what I'm going to do is, once again, I'm going to take my picture, cut it out, and paste it onto my notes here. Okay. So you notice that again, your disc, your circles, you're stacking them up this way. You're stacking them up vertically. So this is a dy problem, right? So it's going to be volume equals pi r squared dy, right? In terms of the y values, from where to where am I stacking? I'm stacking it from 1 to 3. 1 to 3. It's a huge difference if you are doing this dx versus dy, right? Okay, what about my radius? Well, again, look at your picture. Your radius is this distance right here, but my function will only give me this distance right here. So that is why we need to use my axis of revolution as my right function. This is my right, and then it's going to subtract this one as my left. But the problem is this equation is bad again. This equation is written in a way that I can't use it. I got to write it as an x equal function. So first I wrote it as a y equal function to graph it. Now I'm going to write it as an x equal function so I can use it in my integral. So as an x function, if I add the y over, it becomes y minus 1. So my radius is right minus left, which is 2 minus y minus 1. So again, make sure your parentheses are in because you want to make sure you clean this up beautifully. And so 2 minus y minus 1 gives me a nice 3 minus y, right? So that is my radius of 3 minus y squared. Okay, now every variable matches, right? My equations, my integrals in terms of y, my equations in terms of y, my intervals in terms of y. Everything has to be the correct variable. Okay, so that's another checkpoint for yourself. Okay, now I'm ready to go ahead and multiply this out. I gotta multiply out 3 minus y squared. So it's y squared minus 6y plus 9 dy. You have to get comfortable with multiplying these out. Okay, now antiderivative y cubed over 3 minus 6y squared over 2, so 3y squared plus 9y evaluated 1 to 3. This time I don't have a shortcut, so I have to work this all out. So I get pi multiplied by 3 cubed is 27 over 3 minus 3 times 3 squared is 27 plus 27 minus 1/3 minus 3 plus 9. Okay, so I get pi. So 27 over 3 minus 1 over 3, that's 26 over 3. Negative 27 plus 27 is 0. Negative 3 plus 9 is 6, so minus 6, so minus 6 like so. So I get 26 minus 18 over 3, because 6 over 6 is really 18 over 3. If you subtract that, you get 8 pi over 3. Okay, now, just for our learning purposes, I am going to show you that geometry can help us. This is a cone, right? We know this is a cone with a height of 2, because it's from 1 to 3, and a radius of also 2, right? Because its radius is from this to this, right? That's a base area, base radius. So back in geometry, volume is 1/3 pi r squared h. So I get 1/3 times pi times 8. My volume is 8 pi over 3. Beautiful. Now let's shoot. If I know this is geometric shape, could I just go ahead and use geometry to do this? Yes, you can. Absolutely. I would strongly recommend you use it to check like we did here and not use it to solve, because chances are you're not going to get one that is geometrically sound like so. Okay. All right. That's it, guys.